Alright, hi everyone. Welcome to my YouTube channel, City of Electrons. And in this video, we'll do the second thing in the past question. This is the first one. Now, the second past question here is this, saying that let's just open this up. Okay, so it has been observed that epileptic energy supply, that just means unstable energy supply, is crippling businesses in large coastal communities. A client wants to set up a phone charging, that's 100 Android phones. Okay, so this is the load. A phone charging hub and a barbing salon for rechargeable clippers in a shop. Guys, from this point already begin to identify our load. What we want to power: 100 Android phones. 100 Android phones. iPhone users more than which person? So 100 Android phones, and then uh, and then four clippers. Okay, so 104 items. 104 items. But the power, how much power will this consume, and how much power will this consume? We'll have to know them separately, okay, and then add them together to know the total. But that addition sign, look one kind. Add them together to know the total load we need. Okay, so a client wants to set up 100 Android phones. Please, it can be Android, it can be iPhone, it can be whatever phone. Okay, don't worry about that. I don't know why this question just says 100. So then where are we? Hub and a barbing salon, 4 rechargeable clippers in one shop. Okay, so use your knowledge of solar energy to provide a solution with the aid of suitable diagram or diagrams. Explain the design process associated with it, stating your assumptions. Now, this is one thing we have to bear in mind: stating your words, assumptions. Let me just even do this assumption. Okay, now assumptions. No. I meant for this. Yes, assumptions. Then these guys, this is our load. Android, 100 Android phones, 100 Android phones, 100 Android phones, and then what? 4 rechargeable clippers. These guys are the load. Show. All right, so load. Now this assumption is this: the importance of why we have to highlight assumption is that we are not giving, in the look at the question, we are not giving the values of Android phone. That is 100 Android phone, yes, but one Android phone, what is the power consumed by one Android phone in order for it to charge? What is the power for one rechargeable clipper to charge? How much power will one clipper consume? Okay, how much power is required to charge it or to power it? Yeah, let me put it that way. So it is not stated. Therefore, we are to give our own assumptions and then state the assumptions. Do we get it? So assuming we have assumption, let's start with assuming we have the real life clipper right here, and somebody says, okay, I want to open a shop, and I don't trust NEPA. Okay, so I want a solar system to power my this and that. The Android phones, look at the power rating of the Android phones, the maximum power rating of the Android phones I want to charge. 100 of them. Then for the clippers, look at the power rating, so 4 of them. But this one now, we do not have the power rating of any of the item we want to power. We just have the number of the items, so we are going to assume their values. Exactly. But when we assume, we maintain that assumption from beginning to the end. Now this solution here, okay, so in order to design an independent off-grid solar power system, we need to what? No, brothers, right? No, What do I know? We need to know how much load the system is expected to handle. Do we understand it? You want to provide power for something, you should know how much power that thing needs. Okay, so this will help us in selecting the components that meets the required was rating. So to know, that is to calculate the needed power for 100 Android phones and 4 rechargeable clippers, we need to what? Identify or assume the following. Now these are our assumptions. So let's assume that average Android phone charging power is just 10 watts. Okay, so we need 10 watts in order to charge an Android phone. Let's just assume that. We know some will take more than that, some will take less than that, but let's just go with that. It's an assumption. In your own solving, you can take another assumption. Okay, just browse and look for the average power required to charge an Android phone. You can see that online different values. You can take the average and work with that. So I'm going with 10 here. Then charging duration per day for Android phone, 6 hours. Some phone maybe we charge less than that, some we charge faster, some we charge slower. And note that we are charging 100 phones, not one. So somebody might bring his phone to charge in the morning. Okay, maybe 2 hours later another person will bring his phone. Then 30 minutes later another person will bring his phone. So all the phones together within the range of 6 hours, we should be done with them. So let's just say the owner of the shop will be charging phones for 6 hours. Okay, then rechargeable clipper charging power 15 watts. Okay, this one is not really okay. Rechargeable clipper, yes, rechargeable clippers, we have them. So just like as we assume for this one, we also assume for this. As we assume for the duration of charging Android phone 6 hours, we also assume for duration of charging the clippers 4 hours. Then the average sunlight per day equals 5 peak sun hours per day. What does this thing mean? We know we have 24 hours in a day, but we don't have sun through that 24 hours. Okay, we don't have sun through the 24 hours, of course. And even during the day where we're supposed to have sun, some days we have the sun is really it supplies enough, the energy we expect from the sun, like real good enough energy. That's the peak sun hours. Good enough energy can last for like maybe 5 hours, 3 hours, 4 hours or so. You understand? So let's just take 5 hours as the peak sun hour. Yes, we know the place is bright, we can see each other during the day, but there's a period, there are times during the day where we really have good sunlight. I believe you understand that. So, so average sunlight available per day. That's what we mean by peak sun hours per day. Then system voltage. Since we are going to power 100 watts, 10 Android phone. What am I saying? 100 Android phones with 10 watts per Android phone. Okay, and then for the clipper, 15 watts per clipper, which is 4 clippers. So we are going to take this one 48 volts as the system voltage to supply all of them. Okay, now inverter efficiency. Remember that inverter is to convert this the what comes from the solar to the battery, that's DC. But what the phone needs to charge and the clipper needs to charge is alternating current, AC. So we need to convert, and the inverter does that conversion from DC to what? AC. Okay, so let's say the efficiency is not really 100%. Is anything 100% efficient in life? So let's just say approximately 90%. So maybe due to some losses and things like that. So now the load calculation for the phone charging. Remember the load, we set 10 watts for each phone, right? And there are 100 phones. So the total load for the phone will be what? 1000 watts. Then the energy per day, we said this phone will be charging for what? 6 hours. So 100 watts times what? 6 hours. This is the energy we need per day. Are we clear? Then this is for phone charging. Then for clipper load, we do the same thing. Total number of clipper is what? 4 clippers. And the power is what? 15. So that will give us what? 16 watts. How many hours did we say clipper charging will last? 4 hours. So 4 hours times the 60 watts. That's give us the energy per day. Okay. So the total required energy will be what? The phone energy, which is this, plus the clipper energy, which is this. That gives us our total energy we need per day. Of course, considering system loss, we now add 20% of the total energy. System loss in the sense that this is the energy we need per day, is that not so? But for we to supply this energy, understand that we might have losses along the way. So therefore, the energy we need to supply should even be more than this one. Okay, should even be more than this 6.24. So we now consider if we have losses of 20%, 20% of what? Of this thing is what? This is the number. Okay, this the total energy we calculated, right? Total energy. I just wrote it. This one I just wrote. Oh boy, these are total energy. I just wrote it in what? Kilowatts, which is divided by 1000. So total energy. So 20% of this, look at it, 20% of this equal to this now. So now we add that 20%. Look at this. This is our energy we calculated per day. So we now see 20% of it. Look at the 20%. Add that 20% to it. We now have this. So we are going to be working with this one instead of working with this exact energy we need. This is that energy we need, though, but instead of working with it, consider losses. So we add 20% of itself to itself. 20% of this is what? Look at it. Add that 20% to itself to give you a new energy to work with this energy, so that in case there are losses, no problem, we are still providing more than what is needed. So selecting, oh, why 20%? Why not 30%? You can use 30, you can use 10. Remember, we are working with what? Assumptions, but intelligent assumptions, okay? So not too much, not too less. So just within a given range. And of course, you can browse about these things. Consider the efficiency of your inverter, browse about that particular inverter, browse about the efficiency and things like that. So let's continue. Yeah, inverter, battery, and other things. Now, so selecting materials according to rating. So for the solar panel, the required solar panel rating is equal to what? The total energy we need per day divided by the total hours of available sunlight. Remember, we said peak sun hours is what? Average sunlight available per day is what? 5. 5. So therefore, for solar panel, we now say required solar panel equals what? This is total energy, right? Total energy required. This is the one we are using. Total energy divided by what? 5 hours. This will now give us what? Kilowatts. This is the power of solar panel we need. So when you go to the market to buy solar panel for this to work, you should ask for a solar panel of power rating 1.5 kilowatts. Exactly. Thus, for a solar panel of 300 watts, the number of solar panels needed will be what? Equal to required solar panel rating divided by solar panel. Now, what is going on here is that the solar panel we have is what? 300 watts. But what do we need? We need what? 1.5 kilowatts. So therefore, we'll now take the 3000 watts panel, a lot of them, not just one, because one solar panel of 300 watts will not give you this. So you take a lot of solar panel. How many panels do you need now? How many panels of 300 watts do you need to get this one? What do you have to do? The required solar panel rating divided by solar panel rating. So this is the one we need. We need solar panel of 1.5 kilowatts, which is 1500 watts. That's what we need, divided by the solar panel rating 300 watts. So meaning that will give us what? 5 solar panels. So 5 300 watt solar panels will give us the exact 1.5 kilowatts panel. But if you get to the market and you see exactly 1.5 kilowatts panel, fine, go ahead. But that would be really, really large, oh guy. So we are using 5 solar panels, each one 300 watts, so that we can meet this value. So solar panel selected. Now what about battery? Now the energy equals to voltage times capacity. Okay, then capacity is equal to what? Energy divided by voltage, just like change of subject formula. So the capacity is what? 7500 watts divided by what? 48 volts. Remember we said that we are using a battery of what? Inside our assumption, we are using battery of what? 48 volts. Then where is this 7500 coming from? It is the energy per day. Look at it. Look at it. Yeah. Total energy per day, we've calculated it to be what? 7.5 kilowatts. Kilowatts. The same thing as saying 7,500 watts. Watt hour, please. Hour. Okay. So that's how we got this value. So when we divide this, we now get this one, which is what? Approximately 156 amp hour. So this will be the capacity of our battery. Now, allowing 1 day backup, and this should be and 50% depth of discharge. So what this thing mean? 1 day backup means if the battery is not charged for 1 day, it should still be working. It should not just go off at once. If the battery is not charged for 1 whole day, it should still be working. Okay, so that's the allowing 1 day backup. Still part of our assumption, allowing 1 day backup. If you allow 2 days backup, you should go for a higher battery. Okay, if you should allow 3 days, it depends on your own assumption or what you want to work with. So, and 50% depth of discharge. What does depth of discharge mean? DOD, depth of discharge. It simply means what is the level of battery? What will be the level or percentage of your battery if you are not charging it and you are using it? So it's discharging. You are using it. You've used it from 100% down to 50%. Okay, so 50%. Okay, depth of discharge. That's just a simple way to look at it. So now we are saying that we want to allow 1 day backup and 50% depth of discharge. So meaning this our capacity we've calculated as this now. Take 50% of it. Okay, so 50% of what required battery capacity equals this. We are saying that, oh, did I say take 50% of it? Sorry about that. We are saying that this thing now, this value we've gotten, which is the capacity of the battery, it should be what? It should be 50% of the capacity we need. So the capacity we need here is unknown. Okay, but 50% of that required capacity should give us this number. Is that clear? Then we now say required battery capacity equals to what? Of course, just change your subject formula. This one, 50 over 100. When you take it to this other side, to become what? 100 over 50. So 156 times what? 100 over 50. And that gives you this. Approximately 300 amp hour. So I don't have the sign for approximation. So that's why I just use the semicolon to, but this should be approximate. Okay. So that is, we can make use of a 4 make use of a okay, we can make use of a 4 volt a 12 volt 300 amp hour battery in series. Oh, so that 4 should be there, that 4. But let me use it like this. 4. Okay, we can make use of 4 12 volt to give you what? 12 times 12 times 12 times 12, that will give you 48. So we should make use of 4 12 volt 300 amp hour batteries in series. Is that clear? So we'll connect them in series, and we'll have this 48 and of course 300 amp hour. Okay, so that's the battery we should make use of. All right, then for our charge controller, note charge controller is just that thing between the solar panel and the battery, to avoid overcharging, to avoid reverse current and things like that, to just control the battery. So the solar panel is connected to the charge controller. Then the battery is also connected to the charge controller, and from the charge controller to the to the load. All right, so the charge controller rating voltage is what? 48. Current we don't know. So but the total power is what? 1500. Is that not so? Total power is what? 1500. Look at it here. Okay, required solar panel rating power is what? 1.5 kilowatts, the same thing as 1500 watts. Now where are we? Charge controller. So but the total power is this, and where power equals to what? IV, current times voltage. Since we don't know what charge controller current is, just do what? Change your subject formula. V goes down, power over V. So I equals what? Power over voltage. Power is this, voltage is this, and that will give you what? 31.25, approximately 31 amps. So we can select a MPPT charge controller of rating 48 volts and 40 amp. That's minimum. It should be more than the calculated value. Okay. For inverter, we already talked about inverter. So for maximum simultaneous power, phones plus clipper. Phone 1000 watts, clipper 60 watts, altogether 1060 watts. So now we add, so this is the power of the power we need, but add 30% efficiency, safety, meaning what we should supply and the power should be at least 30% more than what is needed. Okay, so this was needed 30% more than it. This was needed 30% of this is what, so 30% times what's needed will give you this. So this value will now add it to this one. So maximum simultaneous power equals what, this required power plus this will now give you this guy, and approximately this guy. Okay, so we choose an inverter of 48 volts 2 kilo watts pure sine wave. How come about the 2 kilowatts? This 1400 watts, and it's better we take a watt that is what, higher. So we are not going to fall down to 1000 watts. Better we fall up to 2 kilo and 2. We should not fall down to 1000 watts. We should go up to 2000 watts. 2000 watts is the same as 2 kilowatts. Some of these values just change like this because in the market sometimes you don't see the calculated value, so it's best just take the one above it. Not in every case, okay, not in every case, but most cases. So we choose that pure sine wave. Then the block diagram of this thing is this. We'll get the sunlight here. Let's go closer. Okay, so sunlight, of course, then to solar panel, to charge controller, to the battery, like I said, and then to the inverter, before to the distribution board. From the distribution board, you now have separate parts, breakers. One for phone charging ports and the other one for clipper charging ports or points. Okay, so that's that. Now the system operation, the way the system works is this: the solar panel converts sunlight to DC. Then the charge controller regulates that charging of batteries. Then the batteries store energy. The inverter converts DC to AC, like I said earlier. Then power is sent to the distribution board, and then power is sent from the DB to phone charging port and clipper charging ports. Our block diagram says it all. Okay, our block diagram says it all. Then the advantage of this is that we are what? Independent from unstable grid supply. We are independent from unstable grid what? Supply. Let's continue. Then 2, low running cost after installation. So after you install the solar system, you don't need to buy I almost said kerosene. You don't need to buy engine oil, you don't need to buy fuel, you don't need to buy all these things. Well, after installation, you are just enjoy yourself. Okay. Then environmentally friendly, no noise, generator, no grrr. So yeah, you understand. And no pollution like diesel engine and the smell of diesel and things like that. And this one is even scalable for business expansion. Okay, you can just change some of the maybe battery, inverter, or the panel. You can scale it up. All right. Now, conclusion is that the conclusion is that a 1.5 kilowatt solar panel, solar PV, okay, photovoltaic system, that's PV, photovoltaic system with 48 volt battery bank and 2 kilowatts inverter is sufficient. Yes, it is, to power the proposed charging hub and barbing salon efficiently, ensuring what? Reliable and sustainable what? Energy supply. Is that clear? So that's that for this video. I have question, leave it in the comment section. Like, share, subscribe, comment, and I'll see you in the next video. Thanks for watching, and bye for now.